Welcome to Homework Lib.
Hi, so for this question we are starting with a buffer of a solution corresponding to HNO2 with its conjugate base NO2 minus. And we are told that the amounts of these concentrations for both of these compounds is going to be a 1.0 molar concentration. And we have a 1 liter solution. So that means that we're going to have 1 mole of each at the very beginning of our reaction. So the reaction that we are dealing with, we are adding an acid that is going to react with the conjugate base. So that is strong acid, HCl, it's going to dissociate into H3O plus in aqueous solution, yielding HNO2 in aqueous solution plus water. So now we know that the amount of HCl that we added is equal to 0.1 mole. We know that the final volume is going to be 1 liter because we assume that there's no volume change. So the concentration of H3O plus coming from HCl added, it is going to be equal to 0.1 molar, right? So with this information, we can start with our ice table, which is going to be given directly in molar concentrations. At the very beginning of NO2 minus, I have a 1.0 molar solution. Of the acid, I have 0.1. Of the corresponding acid of the conjugate base, I'm going to have 1.0, and water, it doesn't matter, right? Because it's a pure compound and it doesn't enter into the expression for the Ka. Next up, the amount of change that we're going to have. The acid is going to be the limiting reagent. So at equilibrium, I'm going to end up with 0.9 of the conjugate base. I'm going to have to something close to 0 of H0 plus. And I'm going to end up with 1.1 of my corresponding acid for the nitrous acid. So as you can see, we have a combination of an acid and its conjugate base. So how do I calculate the pH in those cases? That means that we have a buffer and we use the Henderson-Hasselbalch equation. pKa plus logarithm of the base. The concentration of the base in this case is the concentration of NO2 minus divided by the concentration of the acid, HNO2. Now, first thing that you need to notice, the concentration of the acid is going to be larger than the concentration of the base. So we expect the pH to be below the pKa. Now, the pKa can be calculated as minus the logarithm of Ka. The value for Ka that we have is 4.5 times 10 to the minus 4. So the pKa is 3.347, or let's run it up to 3.35. Yeah, 3.35. Okay, so now this equation becomes into 3.35 plus logarithm concentration of the base 0.9 divided by 1.1. So the pH for this solution is going to be a pH of 3.26. As we expected, this pH is lower than the value for pKa, and that is going to be our final answer. And that will be all.